Hey folks, welcome to this episode on atomic diagrams and bonding introduction. So we've seen these before, the Bohr-Rutherford diagrams. They do represent the electronic configuration of an element. And we've all seen these before. We draw our nucleus, we put in our protons and neutrons, we draw the energy levels and fill them with the respective amount of electrons, and then we add single electrons clockwise, and then we double up going clockwise as well. And if we're dealing with an ion, we have to include brackets and a charge. So let's do an example here. Here, if we look at carbon, first thing that we need to figure out is what is the atomic number of carbon. If we draw our little carbon standard atomic notation, we have here is 12 and we have 6. So our atomic number is 6. Now that means that we have 6 protons, and also because there's no charge here, it also means we have 6 electrons. To find how many neutrons, we take our mass minus our atomic number, and we have 6 neutrons. So we have all our information. Let's get going. Now, one other thing that makes it a little bit easier is if you can find what group it is, remember groups going up and down, and what period it is. The periods tell you the number of energy levels. And the group tell you the number of valence electrons. So in this case, when we look at carbon, carbon is in group number 4, so it should have 4 valence electrons, and it's in period number 2, which means that it should have 2 energy levels. Let's see if that's actually true. So let's go ahead and let's draw our carbon atom. So in our nucleus, we put 6 protons and we have 6 neutrons based on our calculations right over here. So let's continue. On our first one, because it has 6 electrons, and we know that from our atomic number, we have 1 and we have 2. Now remember, our first shell only has 2. So we can only fit there. We still have 4 electrons to go. We have to add another energy level to carbon. And again, we go clockwise. We go 1, 2, 3, and 4. So altogether, we have 6 electrons. All of our electrons are taken care of. Now let's see if our prediction was true. Here we said we have 2 energy levels because it's in period number 2, and 4 valence electrons in that outer shell. Here we have 1 energy level, 2, awesome. And in our outermost energy level, we have 1, 2, 3, 4 valence electrons. So that is correct. So if we have an ion, so remember it has a charge because it either gained or lost electrons, we have to make sure that we do a couple of things. Now an anion always gains, it has gained electrons to become here, and it's going to have a negative charge. And a cation is a positive charge because it has lost electrons. So for carbon, carbon can go either way. And let's just start with our nucleus here. So again, we have 6 protons. We have 6 neutrons. We know that we'll have 2 in the outer shell. Now, if it's gained electrons, well, carbon wants to get that full outer shell. It already had 1, 2, 3, 4. So how many does it have to gain? Well, it needs 8 in the outer shell, our outer shell being this one over here. And so it needs to gain 4 more. So we have 1, 2, 3, 4. Now, it gained 4 negative electrons, so the charge is going to be 4 negative. Similarly, if we look at our cation, again, we start off with this. There's 6 protons and 6 neutrons, and we'll have 2 in our outer shell. Now, carbon originally, again, had 4 electrons on the outer shell, but again, it wants to get a full outer shell, and that means it has to lose a certain amount of electrons. Right now, it has 4. Now, it can't. If it loses 1, it's still going to have 3 in the outer shell. If it loses 2, it'll still have 2. If it loses 3, it'll still have 1. So to get rid of this shell completely, it needs to lose all 4 electrons. So let's go ahead and get rid of these ones here. So we'll just have to scratch this out here. Okay. So in that case, what we're left with is all right, here we go. Let's get rid of this. If we get rid of that and we lose out all those outer shells, all those outer valence electrons, we get our inside electron. Okay. Now, what carbon is left with is it's only left with 2 electrons. It has lost 4 electrons. So it's lost 4 electrons. That means it's lost 4 negatives. So that means that it's now going to be 4 plus. All right, now we can also have a different type of diagram. It's called the Lewis or electron dot diagram, and basically it just shows the valence electrons, because the valence electrons are the things that are involved in chemical reactions. So it's a lot more simple because we don't have to draw all the inner electrons, we don't have to draw the nucleus, etc., etc. We simply just put the symbol in the middle and surround it with the number of valence electrons. Again, if you're dealing with an ion, include brackets if it's... So just a word on unpaired electrons. We want to try to maximize the number of unpaired electrons, which is why we go clockwise. We go 1, 2, 3, 4, and then we double up like this. You'll see that carbon has the ability to create 4 bonds, so it should have 4 unpaired electrons. Nitrogen, for example, can form 3 bonds, and it has a pair of paired electrons. And so when we represent that in a Lewis diagram, what we're going to have is we'll have 1, 2, 3, 4, and we'll double up on the side here. So we should have 3 unpaired electrons, 1, 2, and 3, and then a pair of paired electrons. So let's draw the Lewis dot diagram for carbon. So remember, in the center, we're just going to put the symbol C, and we have to figure out how many valence electrons again. Again, remember that we can get this information from the group it's in. Okay, so carbon is in either it's called 4A or 14, depending on the periodic table you have. In this case, it's very easy because you see it, it's 4. If you have the periodic that says 14, then you just take 14 minus 10, and you get 4. So carbon has 4 valence electrons. So we're going to put that in outside the edge around carbon here. And again, we're going to place them in a pattern going clockwise, 2, 3, 4. And that's it. That's the Lewis dot diagram for carbon. Very, very simple. It doesn't show any of the inner electrons, just the outer ones. So again, if we have ions of carbon, we're going to start with our carbon here. And again, we already had 1 electron, 2 electron, 3 electron, 4 electron. Okay, but since we know it's an anion, it has to gain to get a full outer charge, we're going to have to add the 4 electrons that it's gained. And again, in this case, because it's an ion, we're going to have to put a charge. So we put brackets, it gained 4 electrons, so we have 4 minus. If we go back to carbon here, again, we're going to have 1, 2, 3, 4. Now, in this case, because carbon has to lose these 4 electrons, what you might end up getting is you might end up getting something that looks like this. Well, you lost those 4 electrons, so if you kind of erase them all here, okay, if you get rid of this one, we get rid of this one, we get rid of this one, we get rid of this one, you're actually going to come up with an empty shell. So you can draw this one of 2 ways. Depending on what your teacher wants, in our case, we're going to be drawing it simply to get rid of that outer level and show the inner level. So that means that because carbon gets rid of those 4 valence electrons, it only has 2 remaining here. And to show that it has lost something, again, it's an ion, so we're going to have to put brackets. It's lost 4 electrons, so we get 4 plus. Alternatively, some people might see it like this, where carbon just has an empty outer shell, and you have 4 plus. So if we look at this periodic table, this is just periodic table showing the Lewis dot diagrams of the common elements. And what can you see? What can you spot? Let's look at, like, for example, group 2 metals here. We can see that we have 2, 2, 2, 2, 2, 2, 2, 2. Or similarly, when we look at group 16 or 6A, we can have 6, 6, 6, 6, 6, etc. Okay, so what kind of trend do you see? Well, again, like we were talking about before, when you look down a group, members in a group have same number of valence electrons. So when we look at our group number here, in this case, this periodic table uses 1 to 18. In this case, we just take 16 minus 10, and we get 6. Why 10? Well, because the transition metals, there's 10 of them. So in this case, we have 6 valence electrons. The only exceptions to this are helium and hydrogen, at least what we're going to be dealing with. There are some other exceptions to octet rules, and we'll talk about that a little bit later. But remember, helium and hydrogen, they're satisfied with only 2 valence electrons. Helium will only have 2. And if hydrogen was to gain any electrons, it would only gain 1 because it will want to have the same configuration as helium. So going on to chemical bonds, we're going to be talking about this a little bit more. But why do things create a bond? Well, first of all, when we're looking at ions, the reason that some things form ions is because they gain and they lose electrons. Why do they gain and lose electrons? Because they form a chemical bond. Why do things bond? Well, they become bonded to something else because they want to become more energetically stable. When they bond, they usually release energy, okay? And that means that they'll have a lower energy state. And when we talk about bonding, they can do it in a number of different ways. They can share it, if you remember what that is covalent bonding. They can transfer the electrons, which is ionic, or you can have a movement of electrons. Well, in this case, it can be metallic. Okay, so there are a number of different types of bonds. There are more bonds like that. In terms of covalent, we can start breaking them up into polar, non-polar atoms, and they have different intermolecular forces, and that's a different type of interaction and bonding. But the main bonds that we're going to be talking about, covalent, ionic, and metallic, and it all has to deal with our valence electrons. Again, the electrons on the outermost level. And this is why we could actually, when we're drawing our Lewis dot diagram, we can get rid of these inner electrons. We know that they provide shielding and stuff like that, but really the focus here is on those outer electrons. Now in this case, when we look at lithium, lithium only has one valence electron. Helium has two valence electrons, so it's the electrons on the outer shell. It's not one in particular. If lithium, for example, was to gain two more electrons, all three of these would be the valence electrons. So just a little note on that. Now, one of the things that when we're going to be talking about ions and elements, and if they gain or lose electrons, we're going to be following something called the octet rule. And it basically states that the noble gases have 8 electrons in their outer shell, and a lot of the elements want to have the same configuration. So they combine in such a way that they have full outer shells, or what we say, an octet. So one thing that people get confused on is that they say they become noble gases. No, that's not true. They actually have the same electronic configuration, aka they have the same outer shell as a noble gas. But remember that they can't become a noble gas because what represents the identity of an element is the number of protons. The number of protons don't change, it's just the number of electrons that they hold. So they cannot become a noble gas, but they have the same electronic configuration as a noble gas. And when we start discussing this a little bit further, you're going to be seeing that this doesn't always hold up to all the elements on the periodic table. But it does work for things like the halogens, sodium, carbon, nitrogen, oxygen, etc., etc. So again, when we're talking about bonding and to achieve this octet, they can either transfer electrons, so aka when we're talking about ionic bonding, there's a transfer of electrons from a metal, in this case when we're looking at sodium, to a non-metal in chlorine. And you can see that this electron that it moves over to chlorine, sodium has lost its valence electrons, so it has a full outer shell. If we got rid of this outer shell, what we'd see is underneath we'd have 8 valence electrons. Sodium would have this, and it would have 8 valence electrons underneath the shell that it just lost the electrons to. In terms of chlorine, well, it gained that electron. We can see it right here in purple, and it now has a full outer shell. This becomes positive because it lost an electron. This becomes negative because it gained an electron. It can also achieve an octet by sharing electrons, and we know that this is called a covalent bond. So in this case, oxygen, they both have very high electronegativities, which means that they both want the electrons, and they also have high ionization energies. None of them want to lose the electrons. So if none of them want to lose and they both want to gain, what they're going to end up doing is they're going to be sharing electrons. Now you can see that they actually share 2 pairs of electrons, this one and this one, which creates a double bond in case of oxygen. And we can see this once again. We saw this before. Helium has a noble gas configuration of 2 electrons. So if hydrogen was to gain 1, it would only gain 1 to become 2. And we can see that metals, for example, they tend to lose electrons, and they lose enough so they can have this full electron configuration. Again, a lot of atoms in the periodic table, a lot of elements, want to gain or lose electrons to have the same configuration as these noble gases, those 8 electrons, or as again we call it an octet. So for example, phosphorus has a Lewis dot diagram of 5 electrons because it's in group number 5, so we have 1, 2, 3, 4, and 5. So it would need to gain 1, 2, 3 electrons to get that full outer shell, which is why we see it as 3- in this periodic table. So again, they need to gain or they need to lose to get that full octet. There are some exceptions to the octet, and there are many more than these ones, but we can see that different types of elements can be happy with different amounts of electrons. Most notably, remember that that hydrogen and helium are happy with 2 electrons, so they don't need to gain another 6 or lose or whatever. They're happy with 2 electrons and are stable with that. Beryllium is happy with 4 electrons, and boron is happy with 6 electrons. Now, you can also have a different class of expanded octets, and this is something that you'll learn more in grade 12 when you get into d orbitals and hybridization. Some of these elements that are in period 3, basically going on from phosphorus on, they can expand their octet to actually have more. So, for example, when we look at sulfur on the periodic table is in the same group of oxygen, and so what we should see is that oxygen has 6 valence electrons. 1, 2, 3, 4, 5, 6. So technically, it should only be able to hold be able to bond to 2 other species or create a double bond, like oxygen does. But because it has this third energy level, it can actually start expanding into things called d orbitals. And so in our common knowledge, this shouldn't actually happen, but because of this hybridization deal that it goes under, it can expand this octet and actually be stable with more than 8. And then we also have these things called free radicals where there's an odd number of electrons. Again, something that we'll be focusing on next year. What we're going to be going on to next is the type of bonding. There are 2 main classes. There's intramolecular, so bonds that happen within a molecule. So in this case, we have, for example, if we have 2 atoms within a molecule, here we go. This is our little molecule. It's going to be the bonds that happen between the individual atoms. Now, if we have 2 molecules that might be the same, they do actually interact with one another, but they do so in a different type of attraction or forces, and these are called intermolecular. So these would be, for example, little interaction between this molecule and that molecule. So it's attractions between molecules. So inter is between molecules. So what we're going to be looking at is we're going to be looking at ionic, we're going to be looking at metallic and covalent bonding as types of intra, so within the molecule, and later on we're going to be looking at intermolecular, London dispersion forces, dipole-dipole, and ion-dipole, as well as hydrogen bonds, and these being attraction forces between molecules. Thanks guys for watching, see you next time.